Welcome to my Texas workshop. I'm Randy Lammers.
I'm Keevan.
This is Würth Knowing. So Aaron, today's subject is one that's really critical to the fastener industry and to many other industries as well, and that is atomic hydrogen assisted cracking, commonly known as hydrogen embrittlement. Real important subject.
Certainly is.
A window unit falls from a high-rise building because the screws break. A lady on the sidewalk loses her life. A screw breaks in a chair, gentleman leans back in the chair, hits his head, and is killed. One that's very personal to me is I was out in one of our customers' manufacturing facilities doing a tour, and I noticed electroplated inch series socket head cap screws. They were electroplated. I made a big deal out of this and I said, no, you can't do that. We have to do something different. I told them about hydrogen embrittlement. I told them I teach a class on that subject. And I'm back in my office a week later and I get a phone call. And this gentleman on the other end said, Randy, you were in our plant last week and you made a big deal out of this and you said you teach a class. I need you here tomorrow to teach that class. I said, sir, I'm in Houston, Texas. You're up in the Northwest. I said, what happened? Well, heads of a 5/8 socket head cap screw popped off. Head of that cap screw went across the manufacturing plant and through a metal toolbox. The gentleman standing beside that box thought someone had shot a gun at him. If that would have hit him in the leg, would have taken his leg completely off. He said, I'm very serious. I don't care what it costs. We will pay all costs. Make it happen. I need you here tomorrow. So I did. So I'm standing at the front of this conference room and I'm teaching a class to all of their management, all of their engineering crew. And a young lady comes in and whispers in the ear of the head of engineering. He says, Randy, go ahead with your class. I need to take this phone call. He comes back moments later and he said, now let me interrupt you. Our equipment came apart. The heads of socket cap screws went popping. Guide wires went flying, men went rolling down the mountainside, and today I don't know how many are injured or how many are even killed. I need to talk to you about liability. Let me tell you something. You don't want to be there. I'm standing in front of this class and I know the next word out of my mouth is going to determine which side of the courtroom I'm standing on. You do not want to be there. The risk is not worth the reward. This is always costly. You do not want to be there. Do I have your attention? Now, I'm happy to say no one was injured. There was no liability concerns. We found a path forward and we moved on. But it was costly.
Sure was. When you think of a 5/16 wave washer, a Belleville washer, or a spring pin, costs of $400,000, $300,000, tens of thousands of dollars in just recall of equipment to come back. All of that due to hydrogen embrittlement.
And those are simplistic parts that you don't really even think about. Right. That's not heavy bolting, right?
Right.
Those are simplistic parts, so it can happen to any part with high hardness. So what is this phenomenon in which we speak?
It's obvious this is a very complex scientific subject.
It is.
So we're gonna have to take out our vocabulary here. It's gonna get a little bit to get through, but we will get there.
You know, Aaron, you can get on the internet and there are a lot of white papers written on hydrogen embrittlement. There are a lot of scientific speeches, seminars that you can find on this. But I think our goal today is to do this in a more simplistic way, to explain this phenomenon in its basic understanding.
Sure thing.
So let's go about it that way.
Right. So there's two basic types of hydrogen embrittlement. We have external, which is That's going to happen something in service while it's in service, or internal. So, and our focus today is going to be on primarily that electroplating of fasteners of high hardness and in those types of materials.
You bet. So think about this. Hydrogen is around us everywhere. If you had atomic eyesight, you would see these little hydrogen atoms floating around everywhere looking for a place to go. As a matter of fact, what's 2 parts hydrogen and 1 part oxygen?
Well, that'd be water, Randy.
Okay. I love to do that to engineers and watch them go, let me think here. Yeah, it's water. So water's around everywhere. So we talked about electroplating, and electroplating is an electrolytic process of applying metallic substances. We use zinc a lot, or zinc nickel a lot in the fastener industry. So it's in an aqueous solution. And in the process of electroplating, you generate a lot of hydrogen atoms. So the fasteners or the steel that's inside the plating tank has high concentration of hydrogen atoms introduced to it. That's why that's a particular concern. So let's take a look at a real hydrogen cracked brake and utilize that as an example here. So think about this. So I have these hydrogen atoms and they're very, very mobile. I've introduced this high concentration of hydrogen into the molecular structure of the steel, and they're looking for a place to go, Well, think of steel as being grains of sand, if you will, compacted together, and you have these grain boundaries. So if you can just picture that in your mind, that you have these grains of sand, you get grain boundaries. Well, when you apply stress to steel, particularly tensile stress to steel, those grain boundaries will widen.
Exactly.
So now you have grain boundaries now that the steel's been put in stress. After it's been put in stress, you have these grain boundaries widening. Then you have these hydrogen atoms that are looking for a place to go. They find a widened grain boundary. Well, here they come. So 2 atoms make a molecule, and it's like, come on, boys, I found a place to go. Yeah, so they come, here they come. So they generate they locate all in this open grain boundary where the stress is, and what do you think's taking place there?
Concentrated stress for sure.
Concentrated stress, pressure?
A little bit.
Yeah, just a little bit of pressure. So I always like to ask this question. Which is stronger, a candy cane or a piece of chewy taffy?
I guess it depends on your application, but you know, you could look at it from the hardness being brittle candy cane. You might need it, but you might need that ductility also.
So strong, which is stronger?
It's the candy cane.
It's a trick question.
Yeah.
You just said it absolutely perfect, Aaron. The candy cane is very, very hard, but it's brittle, but it's strong
Sure
in
is.
hardness. Also, the taffy is very, very soft, but it's flexible and it's ductile. Now, think about this. That pressure that we're talking about, where all of those atoms are accumulated, think about this. If I create that pressure inside of a piece of candy cane, if I could somehow create that pressure inside that piece of candy cane, what do you think would happen to that candy cane?
You're gonna get a burst.
That's exactly right.
Yeah.
It's gonna blow. And that, we call it a burst.
Yep.
So a hydrogen-assisted cracking is a burst. Whenever your load that's being applied exceeds now the lattice structure of the steel that is cracked open, it will burst. Now, what if I was to do that in a piece of taffy, candy?
Well, I think you probably get a little bit more movement through the taffy, being that it's ductile.
It's ductile. Right. I'm soft. I'm flexible. I can handle it. I'm kind of a cool guy. I'm like that. I'm like taffy, you know?
Sure, Randy.
So why not? So yes, so think of then our hardness. Now what did we just do? We associated hydrogen embrittlement with hardness. So this is where hardness comes into play. Now, we know through experimentation that at about a hardness, now we have scales of hardness. So we look at a Rockwell C scale, and at a Rockwell C scale of about HRC 34.
Right, that's an SAE grade 5 or ISO 898 class 8.8.
Correct.
That range right there.
Yep, in your fastener strength categories, they're soft, they're ductile, they're taffy-like, they're soft candy-like. Okay, now because the hydrogen still goes there.
It does.
But we say that material, and the word we use, it's not susceptible. So it is soft and ductile-like. Now, go over to the other spectrum, and we draw the line at HRC 39.
Right.
Anything above HRC 39, I'm more candy cane-like.
Right. And you've got, those are ASTM A574 socket head cap screws. So going back to the story you told earlier.
Absolutely.
Or the class 12.9 in ISO.
Absolutely. Reach over there and grab that socket head cap screw.
Just
That's
like
my
this.
buddy Steele over there, by the way. My granddaughter made that. This is a socket head cap screw. This is an example of what we're talking about, that of what broke in that story I told you. Now, this particular part, this is electroplated. It has a yellow hexavalent chromate on here, but I can look at the end of that socket head cap screw and I can tell you that this particular steel is below HRC 34. So this is acceptable if you know the hardness of the steel. If this steel was up above 39, so the ASTM A574 specification for socket head cap screws is HRC 45.
Very, very tough.
Yeah, that's why you don't electroplate these parts. So this is an example of what we're talking about.
So Randy, what do we do in the middle?
Okay, between 34 and inclusive of 39.
Right, so you're looking at SAE grade 8, J429 grade 8, or ISO 10.9, class 10.9.
Correct, correct. So we have our grade 5s and our 8.8s that are the tappy 34 category. We have our really hard parts like the socket head cap screws, by the way, property class 12.9. And now we have this middle section, the grade 8 and 10.9. So the answer to the question there, Aaron, is we bake them. So after they come out of the electroplating tank and we've put our metallic product on there, the next thing we do is we put them in an oven at about 400 degrees Fahrenheit.
Right.
Now that's just enough heat that it opens the pores of the steel and allows the hydrogen atoms in there to outgas. We let them sit there so you get your material up to temperature. That's important, by the way, to understand.
Exactly.
That you don't start the clock when you put it in the oven. You start the clock when you get the material up to temperature. Then you let it sit there. We used to be 4 hours, but latest research tells us that's really not sufficient. So we're looking more at about 8 hours plus. Now you let it sit there and let those hydrogen atoms outgas. So there's some controversy here. And here's the controversy, and I want everyone to listen very careful to the Würth position on this. Our electroplating specification, what's that?
ASTM F1941.
ASTM F1941, and on the metric side, ISO 4042.
Right.
They've addressed this a little bit differently. So in that hardness range, there's some controversy here. Those specifications no longer mandate that you bake in those areas. However, we take a little bit different approach to that. So fasteners are manufactured by companies from all over the world who are buying steel from companies all over the world. And there's no mandate that that steel, the manufacturer of the fastener, does a metallurgical examination of the steel. And we know for a fact that product is out there in commerce that has inclusions, it has hard banding, and these are opportunities for hydrogen atoms to be trapped in there and cause this problem. So in testing, in laboratory testing, where they do full examination, micro-examination, they got good, clean, pristine steel,
Right.
yes, I agree with the lab test that upwards to HRC 39, that material's not susceptible, but that's not the real world. So we have taken a stance on this. So we are not in agreement with some of the specifications. Example, ASTM F1941 specifically says that you don't really have to bake.
True.
And we say we do. If you're buying from a manufacturer where you know that they are doing microexamination of the steel, they know they have good steel, they're also controlling the electroplating processes, all of the controls are in place, they're using inhibitors in the electroplating process, they're watching the acidic cleaning actions, then I'm okay with that manufacturing take the full responsibility of not baking. However, you're out there like most of the fastener industry is, you're buying product from the wholesale market, you're sending it out to your mom and pop, local mom and pop plating company, bake the parts. Bake the parts. The risk is not worth the reward. It's not that expensive. Right. Bake the parts. So that's a hard position that we've taken at Würth, and I'd like to see the rest of the industry take that same position.
And so one other thing to note here is that when we're talking about a failure in hydrogen embrittlement, it's a delayed failure.
It is, and that's critical for everyone to understand. So if you break a fastener while installing, that's typically not hydrogen embrittlement. But if you have the fastener fail later, that is a hydrogen embrittlement failure, typically. But we'll, of course, always do a microexamination and look for the intergranular cracking. So it can happen anywhere up to 48 hours. Right. But we have seen incidences where additional stresses are applied that exceeds now the molecular structure of the lattice structure of the steel, and it blows up and comes apart. Right. So it is a delayed failure. That's what makes this so costly and so critical.
Yeah, you don't know right away until it actually happens. So
exactly.
So Randy, let's talk a little bit about environmental hydrogen embrittlement.
Okay, so environmental hydrogen embrittlement is also intergranular cracking, but it's not due to what we call internal hydrogen where it's been put in there during the processes. This happens actually out in the environment. So if you can think about this, so fastener finishes specifically, we're talking about fasteners here today. This happens, by the way, in other steel components, but fastener finishes. So most of the finishes are sacrificial. So in the environment, as that material is sacrificing itself, it's generating high concentrations of hydrogen, and you're right there on the surface.
Right on the surface, right.
So there certainly is opportunity for that hydrogen to make its way into the molecular structure of the steel. So in the corrosion process, so we also refer to this as stress corrosion cracking. In the corrosion process, hydrogen gets generated, and then you end up with the intergranular cracking. So know your environment.
Yep.
Know your material.
That's exactly right. So we look, if we're going to look at material or cutoff, that's going to be in that 34 HRC range again.
It is. Yeah. So if you're in an area where this is a concern, choose materials that are not susceptible.
Exactly right.
That's that hardness situation. So that's really critical on that one. Just kind of leave that for you to know what to do in your applications. So in conclusion, hydrogen embrittlement is a very serious subject. There has been loss of life, there's been severe injury, and there's been failed equipment, all at a high cost. It's a delayed failure. You do not see it in assembly. Based
on the electroplating process, have to be very deeply concerned with any products that are 39 HRC and try to avoid using any electroplating on those types of products.
Absolutely. Follow the ASTM B850 guidelines when you are baking. That'll give you exact guidelines of what to do on the bake process.
That's exactly right. You know, HE, just like you've mentioned, we do need to be concerned also with the environmental side. You know, try to avoid materials that are above 34 HRC. That's the recommended guidelines at this point.
Right. Use non-susceptible materials. There are ongoing investigations on hydrogen embrittlement. It's not completely understood. This is a complex scientific subject. There's continuing research, and we're staying educated on that, and we'll be covering this in further episodes. Hydrogen embrittlement. The risk is not worth the reward, and that's absolutely worth knowing.
If you haven't done it yet, hit subscribe, and we'll see you next time.